Hi, welcome to my YouTube channel Easy Aviation. Here we discuss about the short simple topic about the aviation field. Today's topic of discussion is VN diagram of an aircraft. So VN or VG diagram is made up of two alphabets, as you can see. VN, so V is the velocity of the aircraft and N is the load factor. Sometimes it is called as VG. So V is same velocity and G is the G force. So first let's discuss about what is this load factor or G force. Okay, so load factor N is the ratio of the lift of an aircraft or lift produced by the wings of an aircraft divided by the weight of the aircraft. So now the query will come like an aircraft is flying. As I already discussed in one of my video, there are four forces. One is the thrust force, which is pulling the aircraft forward. This thrust is coming through the engine. There is a drag force, which is the part and parcel of any body. So the friction between the air and the body fuselage, which causes a drag. To overcome this, the thrust force is there. There is a lift force, which is making this object fly in the air, and this is the weight, which is the force which is due to the gravity pulling downward. So to counter that, this lift force is there, and that's how the aircraft is flying. So for a straight and level flight, lift should be equal to weight. So I'll write weight is equal to lift is equal to, we know the formula, half rho v square coefficient of lift into surface area. This is the equation of a lift. So for a straight and level flight, this is the equation. But when we go for the banking, okay, so now if the load factor is lift to weight ratio, then it should always be equal to 1 for a straight and level flight. But since this is a load factor velocity to load factor diagram, so then there should be some cases where the load factor is not equal to 1. This is a case for a straight and level flight only. So let's see this diagram in detail. This is actually an interesting part. So as you can see, this is the front view of a plane which is actually banking or doing a turn, and the turning angle is phi. So if the straight and level flight, if you see, this is the aircraft, and if it is if it is moving in a straight and level flight, there is no angle of banking or turning, but since it is banking, this is the banking angle. So since the aircraft is okay, we'll have a top view. This is, we are looking from the top, and the aircraft is turning. At every point the aircraft is turning. Okay, this is a horizontal turn, not a vertical turn. So this is an aircraft. Okay, it's turning. So there is a radius at along which the aircraft is turning, and aircraft definitely is turning at some velocity. So as we are aware, there is a radial acceleration or the acceleration centrifugal force or the acceleration which is pulling it inward, which we are aware as mv square by r. So this is the force which is written here, which is actually pulling the aircraft inside. Okay, this is the lift force I have just drawn. So lift force is always acting perpendicular to the relative airflow. So if you see the flow is coming from there, so and the aircraft is in a banking condition, so lift will always act in this direction, perpendicular to the relative airflow, which is actually going out from the plane. I'll like draw like this. So the air is going inward. Okay, you might have studied during the magnetism field lines, which is going inside the plane of the book or coming out. So that's I've drawn. So this is the lift force. So this is the weight, which is actually acting perpendicularly downwards. So weight is equal to mg. So if we make a parallelogram here, so this is also weight, and tan phi, this is a very interesting equation. Tan phi is perpendicular upon base. So perpendicular is this, which is equal to this, that is mv square upon r upon w. Okay, so m can be written as w. I'll just write it here. So tan phi, as we have discussed, is mv square by r upon w. So m can be written as w by g, v square by r w. So w cancel. So I'll take another page. Diagram I'll be explaining in a while. So tan phi, as we have discussed, is w v square by r into w divided by w. So w and g, sorry, gr. So w will cancel out. So this will be equal to v square by r g. So from this equation we can understand that for a this phi is the correct banking angle, as in if the aircraft is making a turn in a controlled manner, like there is no slight slip, aircraft is not slipping inside or outside. So for a correct banking angle, there is a specific velocity and a radius. So if we reduce the radius, as I've drawn in the previous page, if the aircraft is if it has to reduce the radius, then it has to go at a higher speed. Or if the aircraft is increasing its speed to balance this phi, if the aircraft is going at a higher velocity, then it can reduce the radius. So either way, it has to make this phi as a controlled as a best turning angle, and this equation governs that. Now coming to the load factor, how load factor comes into play when the aircraft turn. So in the previous diagram, if we calculate cos phi, so cos phi will be equal to w by l. This is cos phi. Cos phi is the base upon hypotenuse. So w by l. So I'll be writing this also on the next page. Cos phi will be equal to w by l, and or we can write l by w is equal to 1 upon cos phi, and l by w, as we have discussed, is the load factor, lift produced by the wing divided by w, and this is the governing factor, cos phi. So let's say if the aircraft is banking at an angle of 60 degree, then l by w is equal to 1 upon cos 60, that will be equal to lift is equal to 2w. So that means the wing of an aircraft doing a bank, my drawing is not, this is the lift. If making a bank angle of 60 degree, then the lift has created by the wing of the aircraft should be equal to twice the weight of the aircraft, as we have just proved out. So that's how a turning or a banking aircraft has a higher load factor, and the velocity and the radius at which the aircraft is making a turn is also governed by a particular equation. Now coming, since we have discussed, yes, that load factor can vary from 1, where the lift and weight is both are equal, to 2 to 3 to 4, depending on the banking of the aircraft. Okay, load factor also increases, as in I'll give you an example. You can do a mathematical equation later. If the aircraft is descending at a very high rate, and then it has to make a turn, or it has to climb suddenly, as in like you have seen in the jet fighter planes, and during doing the high speed maneuvers. So when the aircraft is descending at a very high rate, where the velocity is very high, and then it'll suddenly do a turn. So during that time, load factor goes to 6 to 8 up to 10 also. So now coming to what the topic of the of this video is, that is VN diagram. So VN diagram is, as you can see, velocity is on the x-axis, 100, this is the indicated airspeed IS, that is 100, 200, 300, 400 knots, and this is the load factor, and this is the box in which the aircraft should be flying. Okay, if the aircraft is at a very high load factor and is flying at a very low speed, doing a maneuver, and then the aircraft will stall and fall. Okay, aircraft stalling also has a factor where I'll just write lift is equal to half rho v square CL into S. Okay, so where the coefficient of lift is maximum. Okay, that means, okay, I'll not get into this part, this is another separate topic. So you'll just understand that aircraft has to fly within this region, and if the aircraft fly within this region, the structural integrity of the aircraft will be maintained. Either if the aircraft is flying in this region, the aircraft will stall and fall, and if the aircraft is flying in this region, there is a high chance of the failure of the structure, because the aircraft is designed to operate within this limit only. So this is all which I have explained. I guess you might have got a little bit idea about the VN diagram. Okay, this diagram is always available in the flight manual or the OEM manual, or the book which is provided by OEM, in which the pilot do understand his limit of operations while flying any fighter, or this also applicable for the helicopters also. So in which regime he has to fly, in which area he has to fly. So the pilot has to go through all this mathematical calculation. So at what speed, let's say it is flying at 300 knots, and the load factor, maximum load factor at 300 knots is this, at around 4.5. so at n is equal to 4.5, and at the velocity of 300 knots, so what could be the bank angle at particular radius. So this all calculation the pilot can do with the help of this VN diagram. So that's how this diagram is pretty much important for definitely a high speed aircraft or the helicopters to operate on. So here I conclude my video. If you have any specific doubt, I am sure that I could have left few points over the VN diagram. So if any specific point is there, you please let me know in the comment section. I'll try to make a separate video over it, or I'll do a reply on that query. So here I conclude my video. I hope I had made few points clear about the VN diagram. Thanks to join, and please subscribe my video. Thank you.